Yesterday we have completed some questions on depth first search, right? On depth first search. Basically we are going to the depth first. Let's say this is the tree. We are going to the depth first, then we are coming back, right? Correct. So today also we will cover some more questions on depth first search. Okay, so in the upcoming sessions you will be applying this depth first search on the graph, tree, traversal, okay, and backtracking, correct, DP also, right? So there are two types of DFS, basically this recursive and the iterative. Basically we will be using this recursive one only, right? DFS, and that's all. Let's solve the question. So today's first question is invert this binary tree. Okay, so let's copy this image. Okay, so this is the image. Basically we are given this tree and we need to invert this. Basically the left node will come at the right side, the right side node will come at the left side. Same with this, right? 1 will come here and 3 will come here, right? So if you see, if you take this subtree, or let's say if you are taking this whole tree, what is happening here? We are having the root, right? After that we are having left subtree and right subtree, right? Correct. After that what is happening? The left will come at the right, this basically 2 will come here, sorry, 7, that is 7 and 2, 7 will come here and 2 will come here, correct? Basically we are swapping, right? Left subtree with the right, got it? And if you check this subtree, that is 2, 1 and 3, right? What should be the output? 2 will be same and 3 1, correct? Same with this one, 7, 6 and 9. It should be 7, then what? 9 and 6, got it? So we are having like this currently 2 and under 2, what is it? It was 3 and 1 after swapping, right? And for right it will be 9 and 6. So we have swapped this subtree, right? This subtree, the small one. After that again these are the subtrees for root, we need to swap them. After swapping we will get root as it is, this 7 here, 9 here, 6 here, 2 here, 3 and 1. We got the answer, right? This is the answer. So basically we should start with the smaller one. We will swap the left and the right nodes. After that we will go for the higher one. Got it, guys? If you see in the question, first we are solving this small one, this small one and this small one. After that when they are swapped, or we can say invert, then we will move to the higher one, right? Higher one. Got it? How can we do this? We are having this tree and we are doing what? We are first checking the smaller one, then when they are swapped, they are inverted, we are going to the higher one, the smaller left, the smaller right. How can we do? We can use depth first, right? We need to go to the depth first, we need to swap the elements, then we will go above, right? This is what depth first, right? If we are having the tree, we will go in the depth. First depth, we will swap the elements, let's say null and null, right? We will swap the left and the right. For this it's done, it will move above. Again for this we will swap the left and the right. This is done. Again we will go up, again we will swap this left with the right. So it's simple, right? How can we code this? We are using depth first search, DFS. So how we will do this? See what we can do. Let's say we are starting from here, okay? We will swap this 2 and 7. 7 will come here. We are having 6 and the 9. Got it? Then 2 will be here. What is the nodes? 1 and 3. Then we will move to the next. We will move to the next. Then what is the, it will swap, right? 6 and 9. 9 will come here. 6 will come here. This is the second approach. Okay. Here we will get what? 3 and first. It's simple. When we are going down, we will simply swap the elements. Let me write the pseudocode. Okay. So let's say we are using temp, the third variable. Okay. So let's say we have started from the root. We will swap its left and the right child. Correct. So let's say node temp is there. We need to swap the left and the right child. So root dot left. Okay. And root dot left will be root dot right. Correct. After that, root dot right will be temp. Can we do this? We are simply swapping the left and the right. We will get this, right? 7 here, 2 here. Okay, let me write the code first, then I will tell you. Okay, so we swapped this 2 and the 7. That means the roots left and the right child. Again, we will get this subtree. We will swap these two elements, right? So it will be, we are calling for the left and the right. Correct. So again we will, let's say invert is the function name. We will call for root dot left. Okay. Now what? This we will check for this. We will swap the elements, and again if there are left subtree, more left subtree, it will complete for that, right? So we are going in the depth on the left side, and we are doing swapping side by side. After that, when left is completed, let's say when left is completed, okay, we have swapped this, and we have swapped these also. That is here what? 9 and 6. Correct. Now it will check for this left. Nothing is there. It will go up. It will go up. Again it will go to this right subtree, right? When it will go here. Okay, got it. So invert, after that we will left, we will check for right. That's it. And we need to return the root at the last for this function, invert function. Got it, guys? What we are doing? Let's code it. Okay, we are having what? We will be having base condition first. If root equal to null, return null. Correct. After that we will swap the left and the right child for the current node. Okay, let's swap it. So tree node, it should be tree node using third variable, right? Equal to root dot right or left, anything, let's say right. Then root dot right will be root dot left. Root dot left will be temp. Correct. We are swapping using third variable. After that we need to call for the left subtree, right? We will go in the depth on the left side. After that we will come on the right side for each root or node. So it will be root dot left and root dot right. Okay, we need to return the root. Accepted. Let's submit this. It's accepted. Okay, the simple question, right? We are just traversing the roots, the left subtrees, and we are swapping their left and the right child, and this will follow until we go in the depth and cover all subtrees. Clear for all. What is the time complexity here? On, correct. Okay, so it's on, right? We are traversing each and every node. So if there are n nodes, time complexity will be on. What is the space? Space will be the maximum height of the tree. So if it's balanced, it will be log n. Okay, understood how space is log n, how it's height? Because see, we are going to the depth, right? We are going to the depth. So we are covering one side, either left or right. Okay, majorly left only. So it should be maximum of height. After we are coming back, we are removing the element from the stack, right? It's one call is completed. So maximum space will be the maximum height. Got it, guys? Shall we move to the next question? So the next question is sum of left leaves. Now what is the leaf? A leaf node is the leaf that is the left child of another node. Okay, with no children. Got it? So if you see the example, now here what should be the answer? We need to find the sum, right? Sum of left leaves. What are the left leaves first? It will be left child of the node. Okay, first thing, and no children, should have no children, correct? So this is the left leaf and this is the left leaf. So answer will be 9 plus 15, that is 24. Okay, how will you do this? Can I say we will check for every node if its left is not null, right? And left of left is null and left of right is null, correct? Let's say I'm checking for this node, correct? I will check for its left, it should be not null, right? So root dot left should not be null, correct? And second condition, root of left should be null and its right should be null, correct? Then this will be the left leaf, correct? So root dot left equal to null. Okay, this should be null. And the third condition, root dot left dot right equal to null. If these are the conditions, then we can say this is our left leaf. Okay, and we will add the value of this in our sum. Okay, got it? See, we are here, currently we are at 3. Okay, we will check for the, now let me write the sum also, like we will do sum plus what? Root dot left dot val. Okay, we need to add this value, correct? So we are at 3. We are checking for the for its left child, if the left child is leaf node or not. Okay, first we will check left should not be empty, should not be null, so 9 is not null. Then we will check if this is the leaf node. So these are the condition for leaf node. Okay, root dot left should be equal to null, it's null, and its right should be equal to null, it's null. Then we can say this is the leaf node and we can add this value in the sum. Shall we code it now? How can we code? We will simply apply this equation, right? If this is true, we will having one variable sum and we will add the value in that sum, correct? After that, what we will do? We will call for the left subtree and the right subtree. So base condition, for every recursion you should have a base condition, return 0. Okay, after that we will be having one sum that will calculate the sum of that particular tree, the subtree or the node. Okay, so if root dot left, what was the condition? It will check for the, let me write it, it will check for left node, then it will check if it's leaf node or not. Okay, so first left node should not be equal to null. The second condition is it should be leaf, right? So root dot left should be leaf, so its left should be equal to null, correct? And its right, that is root dot left dot right should be equal to null, correct? If these are the conditions, we can say this is the valid node. We need to add the sum of this node in the sum. So sum plus equal to what? Root dot left dot val. This is the left leaf node. Left leaf node, correct? After that, if this is over, we will check for the next left subtree, right? So we will call this same function, and here we will be calling what? Root dot left, and after left is completed, we will call for the right, root dot right, and we will be getting some value from that, right? Let's say from left from right we are getting what? 15, right? This 15, we are getting 15, so we need to store this. So sum plus equal to this thing, and sum plus we need to add this value in the sum, correct? Value which we are getting from the left subtree and the right subtree. At the end we will return sum, correct? Let's run this. Compilation error, return 0. What is the error? If root equal to null, it's accepted. Let's submit this. It's accepted. Okay guys, got it? How we are doing this? For every node, first it will check for the left leaf. If is it the leaf node? If this is the leaf node, then we will add the value in the sum. Then we will call for the left subtree and the right subtree, and we will be getting some value, the value of the left leaves, right? That we will be adding in the sum, and after that we will be returning that. Got it? What is the time complexity? Again, correct, it will be on. We are traversing each and every node. Space, again it will be the height, correct? The maximum height. Okay, next question. Path sum. Okay, so we are given the root of a binary tree and an integer target sum. Return true if the tree has a root to leaf path such that adding all the values along the path equals target sum. Let's see the example. Okay, so this is the tree given, and target is also there, I guess. Yes, target is, let's copy this whole thing. Okay, so we are given the tree and target is 22. Okay, now we need to find a path that sums equal to 22, path from root to the leaf node. Okay, it can be either this, it can be this, right? It can be this, it can be this, correct? These all are the path from root to leaf. Now what we need to find? We need to find the sum of nodes, and this path is equal to target. Okay, this thing we need to find. How can we do this? Okay, let me explain. See, what we will do, we will apply DFS, correct? As we go down, see, we will go here, let's say. Okay, we are at, or let's say we will go to down, correct? We are at 7 now, but while going we will be checking one thing. We need to maintain the target, right? Maintain target. See, let's say we are at this point, right? Now what is the target here? What should be the target? We got some 5 and 4, that is 9 till this point. Okay, what is the remaining sum? it will be target was 22 minus 9. What is the answer? It's what? 13, right? 13. Okay, so remaining sum is 13, right? Now we need to get the nodes whose sum is 13. Let's say we have covered this point also. Now the remaining sum is what? 2, right? Now it will go to 7. It will go to 7. Now what is the remaining sum? It will be greater than it will be negative, right? 11, it will be greater, right? The greater than target, that is 22. Sum is greater than target, so we will move up. We will go up. We will check for the right. Correct. Now here sum was 21, correct? Not 21, 20, right? And adding 2, we will get the remaining sum 0, right? That means we got the answer. Understood? I think bit confusion. Let me explain it again with proper notes. Okay, so we are at here. Okay, so we will be calling the function. In the function, let's say we are having the function in which target is there. Let's say in the function the root is there and the target is there, right? This was the given function and target was 22, right? At this point. Okay, we will start. We will add 5 and we will call this left, correct? So we will call root dot left with what is the target now? Minus 5, 22 minus 5, right? 5 is already included. Now we need to get the target. What is the target? 17, right? So this will be the target for this, right? Got it? And when we move next, again root dot left, what is the target? Minus 4, it's 13. Understood, guys? What we are doing? We are correct, we are doing the same thing. We are basically calling the function with target minus root value. That means this root, this node, we got it. We add in the target, that means the path sum, and now we need to find the roots with total sum target minus root value. Understood, everyone? While going down, we are just subtracting the node value from the target. That means this node is included now. We need to find the remaining sum. Yes or no? Understood the intuition? And whenever we will get, we will now the question is when to stop. When to stop? We need to find the path from root to leaf. Okay, so whenever we will get, let's say root dot left equal to null and root dot right, basically we need to check for the leaf node. Okay, equal to null. When we get this condition, that means this is the leaf node. Okay, we got the path from root to leaf now. Okay, we got the path from root to leaf now. Now we need to check what? The target sum, right? The target sum should be equal to 0. Correct? This thing we need to check. If it's equal to 0 or the root value. Basically root value also we need to include, right? Means after that it will be 0 only. Correct? You got the intuition, everyone? If it's equal to true, we will return true. If you see this, what is the confusion? If you see the, like we are starting from the root, right? The initial target was 22, right? After that we are calling for its left. Okay, in the DFS we will call the left. Okay, we call the left. After that, what should be the target now? We got this 5, we added this 5, so we will remove this in the from the target, right? So from the target we will remove this 5, that means 5, we got it, right? We add in the path sum. Okay, we added path sum. Now the target is 17. Again, when we are done with this node, we will call its left. Again we will say we added this 4 in the path sum, we will remove from the target. Okay, That means at this point we need 13 target. Okay, that means 13 path sum, 13 as the sum of nodes till leaf node. Understood? We can also maintain this path sum as we are going down. That will be another approach if you are thinking of that, right? Let's say we have completed this 5. We will add in the path sum plus equal to 5. When we are done with this 4, we will add 4. Okay, the target will be same. And at the end, when this is the condition, this leaf condition, right? We will check if target is equal to path sum. We will return true. Okay, just I'm not using this extra variable. I'm doing this with the target sum only. Okay, interviewer will be happy. Our work is to make interviewer happy so that he will give the job. Got it? Shall we code it? Let's code it. Okay, so what is the given? First, base condition, right? If root equal to null, return false, right? That means path sum, path is not there, right? After that, if, now what was the base condition? For every root we need to check if this is the leaf node or not, right? If root dot left equal to null and root dot right equal to null, if this is the leaf node, we will check if target is equal to target sum is equal to that root value, that root dot val. That means we got the path, right? We got the path whose path sum is equal to target sum. We will return true. Correct? Otherwise, return false. Correct? So this is the condition we are checking for leaf node. If it's a leaf node, we got the path, right? We got the path from root to leaf node. Then we need to check if path sum of all nodes is equal to target. If this is the case, then we can say true, otherwise false. Okay, so next we will call this, we will call for root dot left. Now we need to return we need to subtract this value, right, from target sum. What we need to subtract? Root dot val. Correct? Same with, after left is completed, then we will move to the right. And one more thing, see, at this point our target value will be in the minus, right, will be negative. So when it will move up, right, so for this call, what was the target value? It was 13. So it will retain this 13, not the negative value, right? And it will call with 13 value for this right. So if you see in the question, let's say we got the value negative, right? At that case, it will return false. It will go back and we will be completing this root dot left. Then it will go to the root dot right with the value which we are having at the root. That means in this case it was 13 and call for this 2. Okay, and we need to maintain this also. Let's say it will return boolean left node equal to this thing, and boolean right node will be this, and at the end we will return what? what we need to return. If either of this is true, we can say it's true, right? So we can say left node or right node. If either of them is true, then we can say we found the path with some target. It's accepted. It's completed. Okay, so I hope everyone understood the approach. You can see the approach. Okay, if it's false, call for left subtree and right subtree, and we can say if either of them is true, return true. Correct. Let's say first we will cover all the left side, then we will cover the right side, the DFS basically, and we are checking this condition for every node. That means if this is the leaf node, our target sum should be equal to the root value, right, which we are keep subtracting. Everyone clear? So the next question is balance tree. Right, now we need to check if the height, basically its height balanced or not, and height is basically it is a tree in which depth of two subtrees never differ by more than one. Okay, how can we do this? Subtree, right? We need to check for two subtrees. How can we do this now? Let's say in this case it's not like the height difference is not more than one, right? It's one only. So here we can see. So if you see the example here, the height difference, the height for this is 1, right? And what is height basically? In which the depth of the two subtrees of every node. Okay, so what is the depth of this subtree? Let's say it's 0, right? For this it's 1 and 2, correct? So it's differ by 2 greater than 1. So we can say this is not balanced, right? This is not balanced, correct? How can we find this? We have done one question, that is maximum depth. Same approach, can we apply this? Yes, we can apply. Where we can apply this? We can apply for the left subtree for every node and right subtree. Right subtree, correct? We can get the maximum depth for left subtree and for the right subtree, correct? Then we can check if their difference is greater than 1, we can say false, correct? So now we need to implement this logic for maximum depth, and this will be in the helper function. Okay, see, for the balanced subtree we need to check what is the definition for this. The definition is the depth of two subtrees of every node may never differ by 1, right? So we can write it here. Okay, so this is the definition, right? What it's saying, the depth of two subtrees for every node, we need to check the depth. Let's say we are at this node, we will check the depth of this subtree and this subtree, right? The depth of two subtrees of every node may differ never differ more than 1. Okay, so its depth is 2, its depth is 0, so we can say it's greater than 1, so we can say it's not balanced, right? So how to find? For this we need to find the maximum depth for left subtree and the right subtree, correct? So what is the logic for maximum depth? We are going in the depth, right, and we are adding +1. When we are returning, we are adding +1, correct? For that it will be null, right? We will add +1. Again we will go here, we will add +1, that is 2. For here we will add +1, that is 3. So till now it's 3, and when we will check here, it will be +1. So here we get +1. So 3 minus 1 will be 2. So this was the logic, right? We are checking for this maximum depth. Now we need to find the maximum depth of left subtree and the right subtree. So one approach is this one, right? So what we can do, we can get the maximum depth for every node for their left and the right, right? So let's say we are at this node, we will call the function maximum depth for left and the right. Okay, we will get the answer. After that, again we will go to this node. Now this is our node. Again we will call the maximum depth for this and this. Okay, now again see what we are doing here. For while we are calling this maximum depth for this node, and that only we can get the maximum depth for this node also, right? But in this situation we are calling again and again, right? This will take the time complexity. Let me write the code. Okay, first let me write the code. So first approach was we will get max depth for left and right subtree for every node, correct? After that, second part is we will be having one function max depth, right? So basically it will take n square time complexity, because this function will take n, right? It will check all the nodes and we will get the maximum depth for this, correct? But while we are at this node as root, again we are checking for this, right? Again it will call the max depth with n by 2, right? After that n by 4, but ultimately it will be, after adding, it will be n square only. This is time consuming, right? We can get the maximum depth for each node at one iteration only, that means O(n) time complexity. You understood? The first approach was this one, right? We are going to each and every node, then we are calling this max depth for its left and the right subtree for each and every node. We have covered like, let's say for this node we have called this and this the max depth. Again when we are this node as a root, we will call this, because but it was already covered with this one, right? Let me write the code for this, right? So is balanced. First we will be having basically three functions will be there. First is this one only, then the helper function in which we will be basically checking if it's balanced or not, the left and the right subtree. Okay, so for this the base condition will be root equal to null, return true, right? If it's null, then we can say it's balanced. Otherwise, let's say we are having one function return what, height check or check height, in which we will be passing the root. Let's write the check height, boolean check height tree node root, correct? And this basically what we are checking, we are checking the height of the left and the right subtree, right? To check the height of left and right subtree. How can we do this? First the base condition, right? root अगर null है is equal to null, return true. Otherwise, now if what now we need to find the, we will call the function, right? One more function will be there, let's say for finding the depth, finding the height, find height, correct? Tree node, let's say node, correct? So we will be calling this function for left as well as for the right subtree, right? So if find height or let's use variable left height equal to right height what root dot left subtree and right height equal to root dot right. We will get the height, the depth of the left and the right subtree. Now we need to compare the we need to find the subtraction, the difference, right? But we don't know which is greater, right? So we will be using math.abs here. Left height minus right height. Correct. If this part is greater than 1, we will say it's not balanced and return false. Got it? After that we need to call for the left and the right, the same function, right? The further subtrees, right? The left and the right. So return check, again it will be returning the true and false, right? But both should be true. If either of them is false, we will return false. So AND operator we will be using here, height root dot left, correct, and check height root dot right. Got it? Here we are checking the height of left and right subtrees for each and every node. Correct. If it's greater than 1, if at any point is greater than 1, return false. Okay, otherwise call for left and the right subtree. Correct. Now find height, find depth. It's easy. We already did this part. If node is equal to false, not false, null, return what we need to return, it's int, return 0, right? Otherwise we will get the left height. Okay, sorry, we'll get left height node dot right, that is equal to node dot right. Correct. After that, what we are doing in the after the step, we are returning maximum of both plus 1, right? 1 plus math.max left or right. Correct. Let's run this now. It's accepted. Okay, so understood the approach. What we are doing, first we are checking with the root and it will check for its left height, that means the left depth, the maximum depth, and the right, correct, and then we will calculate the difference between these two subtrees. If it's greater than 1, we will say false, it's not balanced. Otherwise we will call the same function with the left and same function with the right after completion of left. After completion of the all left subtrees, we will go to the right, and if we ever get a false, it should return false. That's why we are using AND operator, correct. And in the finding the maximum depth, we are using this logic. We are simply getting the left and the right height, correct, and we are adding plus 1 as we did here. See, when we are returning, it will be having one null. So here null, right, when it was returning, it will return plus 1. Same with this, same with this. So that's why we are adding plus 1 and maximum of both left and right, because we need to find the maximum depth. Understood everyone? Now this is checking n square time complexity. Why? See, when we are at this node, the root node, it will call for this, right? Call for this, and we will call the max depth function, finding the height. Find height. That will take on time complexity, right? So on for this, right? And this is the first call. After that, when we will be at this point, again it will call for this and this subtrees, right? Maximum depth, finding height. Again it will take, in this case it will be n by 2. In the next iteration it will be n by 4, but ultimately it will be on square, correct? Multiply. Got it? Understood? This is not the optimized approach, right? Because we are taking this n square time complexity. But we can find the maximum depth of each node with this one iteration only, right? While we are going down, while we will go up, we will be having this maximum depth, right? For each node. Understood this point? Checking the maximum depth in one iteration, we will get the maximum depth for each node as we are going from depth to the up to the root. Understood, guys? This approach was clear for everyone, right? This one, n square time complexity. And you understood how we can do this in one iteration, how we are getting the maximum depth for each and every node in one iteration, because while calculating the depth, we are going from down to the up, and for each node we will be having the maximum depth. That's why we are adding +1 to that for its parent, right? See, if you see here, we are adding what? We are adding +1 to the depth for its parent, for its root. Okay, so we can do this in on time complexity. How? Let's write the code. Let's modify this. Okay, let's say instead of this function, we are doing everything in this function only. How? Let me write this. Okay, so let's comment this out first. Okay, so we will be calling find height, correct? Root for root we have called this function. In the root, what we need to do? We need to do these things. After that, we need to check this condition also here. This condition, right? This condition for if length of left and the right is greater than 1, at that point we will return false, correct? So if base condition is there, then we are calculating the right, then left, then here if what the difference math.abs what left and right, correct? If it's greater than 1 at any point, we will say return. Now here we are returning what? Int. So let's return -1, correct? Okay, so here it's here also it will be same, correct? The left and maximum of both. But one more thing we need to check. Here we are checking this condition also, right? At any point, if we got null, the false, we will return false. So here we are returning -1. So let's have the condition for this. If left is equal to -1 or right is equal to -1, that means it's already false. Okay, and we can say return -1. Got it? And here also we need to check if find height is equal to -1, we will return false, otherwise return true. Okay, understood? These two conditions we need to add here only. Okay, so for that we are calculating the height difference between the left and the right. If it's greater than 1, we need to return -1. And for further let's say for further, like if we going up, right? If you see here, first we are calculating the last one, right? Null. Let's say here only we got -1, here only we got -1. The difference is there. Okay, so while we are going up, we need to return this -1 only. Okay, -1 for left, so that we can get to know that yes, it's not balanced. Okay, and again it will return -1 only. So we need to maintain this part. Okay, so here we are checking this and condition. Here we are using this -1. If either left or right is -1, that means is not balanced, and return -1 only. Okay, so that for upper trees it should get -1. Got it? Means it's not balanced. Let's run this now. Okay, it's accepted. We can also submit this. Okay, it's accepted. Understood what we are doing here? Just instead of calling this finding maximum depth for each and every node, we are just calculating it once, and we are finding the height for left and the right subtree at once and finding the difference. If it's -1 somewhere, we will return -1. That means it's not balanced. At the end we will check. If it's -1, we will say false, otherwise true. Just simple code, right? It is just the modification of that maximum depth, right? Just we are checking this condition, these two conditions. That's it. For this, time complexity will be O(n), right? Because we are traversing each node only once. Understood for everyone?